It's a great pleasure to speak. And it's the first time that I'm speaking at CRM and not giving a Blackboard talk. Usually I enjoy giving a Blackboard talk. So I'm going to talk about a topic called S-Brane Cosmology. And this concerns the question whether time is past infinite or not. And you probably know that according to the Penrose-Hawking theorems, there are singularities. And if you apply the Penrose-Hawking theorems to standard cosmology, you find that that universe began with a singularity, and that therefore time was not past infinite. And what I will show you is that with this object called an S-brane, you can circumvent the Penrose-Hawking theorems, and you can get a cosmology where time is infinite in both directions. So this is the topic, and oops, good. So I'll first motivate the discussion. I'll put the discussion into context. This will take quite a bit of time. Then I'll introduce the specific model, which is the S-brane, and I will also mention what I mean by ekpyrosis. And if I were speaking to a cosmology audience, then part 3 would be the most important one, namely the part where I take this model and I derive predictions for observations. But since this is more of a mathematics audience, I will just discuss it very briefly. So this is a menu for this afternoon. Okay, good. So the context of the discussion is classical general relativity as a theory for space-time. So space-time is a pseudo-Riemannian manifold with a metric of signature 1, 3. And matter is taken to be either a classical perfect fluid or a classical scalar field. So both space-time and matter are described using classical physics. Now, the metric obeys the Einstein field equations. So the Einstein field equations, hopefully you see my cursor. So the Einstein tensor, which depends on the geometry, is equal to 8 pi g, g Newton's gravitational constant, times t mu nu, and t mu nu is the energy momentum tensor of matter. So this equation is an equation which this metric has to satisfy, and it tells how matter curves space-time. So if you take a classical perfect fluid, then the energy momentum tensor is given by the energy density and by the pressure and by the fluid flow velocity. So if you have a gas of particles at rest in an expanding universe, then the u mu has components 1, 0, 0, 0. So this is the context. And now in cosmology, we are usually interested in very simple situations. We are interested in homogeneous and isotropic spacetimes, spacetimes for which the metric is given in this simple form by dt squared, physical time. These are the spatial coordinates which expand as the universe expands. And this a of t is a scale factor which describes how space expands. So in cosmology, we are interested in this homogeneous and isotropic background, and we are interested in linearized perturbations of the metric and of matter about this background, because it is these linear perturbations which are being observed now in observations. So the linearized perturbations satisfy the linearized Einstein equations. So the linearization of the Einstein tensor about the background metric is equal to 8 pi g times the perturbation of the energy momentum tensor. So these are the things that we are interested in cosmology.
Robert, do you have a question? John would like to ask you something.
Go ahead.
John? John? He doesn't seem to understand.
Sorry, I turned it off. Robert, the dx squared, is that a flat 3-dimensional metric?
I will take it to be a flat three-dimensional metric, and the reason is that today the universe is almost spatially flat, and therefore in the early universe it was very close to spatially flat. But that's just an approximation, that's to simplify notation. Good. So now Hawking and Penrose proved a theorem which states that if the metric and the matter is a solution of the Einstein field equations, and if matter obeys this energy condition, the dominant energy condition, which says that energy density plus 3 times the pressure is greater or equal to 0, and if there are no closed time-like curves, then there are time-like or null singularities are unavoidable, and that means that time cannot be continued to infinity in one or the other directions. So now this dominant energy condition, from a classical point of view, is very reasonable because the matter that we know of has positive pressure. And so this essentially means that if you have positive energy density, then the dominant energy conditions are satisfied. But you will see that something that violates this energy condition is going to be very important. So, good. So an application, the first application of these Penrose-Hawking singularity theorems is to homogeneous and isotropic cosmology. So in standard Big Bang cosmology, we assume that matter is a superposition of classical cold matter, which is a pressureless fluid, and this is dominant at late times. And the other component is radiation, the microwave background, which has positive pressure. Pressure equals 1/3 energy density. This dominates at early times. And at early times, this matter implies that the scale factor grows as t to the 1/2. And this implies that if you go back to t equals 0, the scale factor is 0, which means the energy density is infinite. That's a Big Bang. Singularity. And here I defined the Hubble expansion rate, which is the derivative of A divided by A. Sorry about the tech error. So the second application of the singularity theorems is to inflationary cosmology. Inflationary cosmology is the paradigm of early universe cosmology today. So in inflationary cosmology, you assume that matter is a classical scalar field with a positive potential. For example, the potential, which is 1/2 m squared phi squared, quadratic potential. Now, the equation of motion for a scalar field in an expanding background is this Klein-Gordon equation with a friction term, which comes from the expansion of space. And this is the derivative of the potential. So the energy momentum tensor of a scalar field with potential energy is given in this form, the energy density and the pressure. And I wrote these expressions for homogeneity. So I neglected the spatial gradient terms. So if you neglect spatial gradient terms, then the energy density is kinetic energy plus potential energy, and the pressure is kinetic energy minus potential energy. Now, inflation is the hypothesis that the scalar fields start at a very large value, much larger than m Planck. And then if you look at this equation, h is very large. Therefore, the scalar field will roll very slowly to the origin. And while it's rolling very slowly, this term is negligible compared to this. And therefore, you get pressure, which is approximately minus energy density. And so if we go back a couple of slides, you see that this violates the dominant energy condition because pressure is approximately minus energy density. So therefore, you might actually assume that in inflationary cosmology, you might be able to avoid the Big Bang singularity. But this is not the case, because this phase of slow rolling is bounded both in the past and in the future.
Robert, there's a question by John. John, would you like to ask it now? Turn your loud microphone on. Go ahead.
Yes, actually I had a previous question which you already answered, had to do with the sign of P. But I have another question. In the dissipative term for the scalar field, presumably H is positive, so it's really
in
decreasing.
an expanding universe, H is positive.
So isn't that, I mean, phi is going down like an exponential.
It's going down, but not
So
like an
why is that
exponential because of this
inflationary rather than
dissipation.
deflationary?
Sorry?
Why is it inflation instead of deflation? It seems that the amount of matter is reducing, not increasing.
Yes, the amount of matter is decreasing very slowly if the field is rolling slowly. So inflation is the fact that A of t is growing exponentially. And this comes from the Einstein equations.
Oh, so I'm sorry, I'm not a relativist, but I just know it as an amateur, but I thought inflation meant that as the universe is expanding, somehow or other the total amount of matter is increasing.
The total energy is increasing,
Right.
but the energy density is not increasing. But really what's important for inflation is that the size of the universe is expanding exponentially. That's inflation.
Okay.
So this is a temporary violation of the dominant energy condition. But if you look in the future, once the scalar field becomes smaller than m Planck, then the dissipation term becomes unimportant and you get fast rolling, so inflation stops. Pressure becomes positive.
I don't want to steal more of your time, but A is increasing. That means the size is increasing. But inflation, for money-wise, it means that the value of the currency is decreasing because there's too much currency. So I misunderstood that?
Well, no, I'm not going to comment on that. I'm just going to say A of t growing almost exponentially, that's called cosmological inflation.
Oh, so it's the size.
It does mean that the total energy density is also increasing approximately exponentially.
Ah, okay.
But the density is not.
Okay, thanks.
Okay. But now the key thing is that even if you go backwards in the inflationary phase, any spatial gradients that were present during inflation become dominant in the past. And they give positive pressure. So there is a pre-inflationary phase, inevitably, and therefore there is a Big Bang singularity also in inflation. Good. Okay. So now all of these considerations were classical field theory, and even classical field theory and quantum field theory is a very bad guide if you come from the point of view of superstring theory. Because in superstring theory, the fundamental constituents of matter are strings and not point particles. And that means that there's fundamentally a breakdown of any effective field theory. And so if you go away from effective field theory, the singularity theorems do not apply. And so therefore there's a chance to obtain a non-singular cosmology. Okay, and so now in what follows, I will give you some heuristic arguments why we should expect a non-singular cosmology if we come from string theory. And then after that, I will then introduce this mathematical object, the S-Brane, and show that you can show the non-singularity even with equations. So first we'll come from some qualitative considerations. So for now, I will assume that all spatial dimensions are compact. I'll take them to be toroidal, radius r. And in this background space, strings have various kinds of modes. There's the center of mass motion of a string, which is the momentum of a string. And the energy of momentum modes is quantized in units of 1 over r. But strings can also wind space. And the more times a string winds space, the larger the energy is. So the energy of a winding mode, which winds m times, is m times r. Now strings also have oscillatory modes. So these are the oscillatory modes of a violin string. And their energy is independent of r. But there is an exponential hierarchy of these oscillatory modes, a huge number. So what happens if we do thermodynamics in an expanding box, given that the box is filled with a gas of strings? So here it's important that there's a new symmetry that emerges, which effective field theory does not have. This is the so-called T-Duality symmetry. So again, these equations I just had before, the energy of momentum modes, the energy of winding modes, and you see that there is a symmetry if you replace R by 1 over R in string units, and at the same time you interchange N and M, then the mass spectrum of string states is unchanged. And this is also a symmetry of the interactions of strings. And if you postulate that this is a symmetry of strings at the non-productive level, then you get the prediction that there should be high-dimensional objects called branes. So this is a key symmetry of string theory. So we have new degrees of freedom and a new symmetry. So let's now look at a box filled with a gas of strings. The box has radius r, and I'm slowly compressing the box, and I'm plotting the temperature as a function of the size of the box. So when the box is large, then the energy will all want to be in the modes which are light at large values of the radius. So they want to be in the momentum modes. As you shrink the box, the momentum modes get heavier, the temperature rises, but once the temperature gets close to this limiting temperature called the Hagedorn temperature, then you have such a high energy density that instead of pumping more energy into the states that already existed, you start to create the oscillatory modes. So instead of the temperature rising, you get equal temperature bath with more and more degrees of freedom. But once the box becomes smaller than 1 in string units, then it becomes efficient for all the energy to drift into winding modes, and then the temperature decreases again. So this kinematics of strings in an expanding box indicates that in string theory, there's never going to be a temperature singularity. So the temperature is always going to remain finite, as opposed to standard cosmology or inflationary cosmology, where the temperature diverges at the Big Bang. So there's a second argument, and the second argument also goes back to an ancient paper that I wrote with Kuhn-Waffer, string theorist at Harvard. So in quantum mechanics, we know that the position operator is given by the Fourier transform of the momentum operator. But in string theory, there's a dual operator to momentum, namely the winding. And so we can define a dual position operator, which is the Fourier transform of the winding. So for each topological dimension of space, there are 2 position space coordinates. So now, if you imagine a poor experimentalist with very little money who's trying to measure length, then if R is very large, the experimentalist will build their sticks, the measuring sticks, with the light degrees of freedom, which are the momentum modes, and therefore length will be measured in terms of x. But if R is very small, the dual experimentalist with very little money will be measuring distance with the degrees of freedom, which are light at small r, which are the winding modes. So for this dual observer, length is measured in terms of x tilde. Now, if r is approximately equal to 1, then the experimentalist is in trouble because neither x nor x tilde is light. And if the experimentalist has enough money and enough energy, they'll have to build measuring sticks which contain both x and x tilde, 2D coordinates. So this means that effective field theory will inevitably break down at the string scale if you come from string theory. And so therefore the singularity theorems will not be applicable. Okay. So this poor observer who tries to measure distance in a box of length L will be measuring the box to have physical distance given by this scale. So there's no distance singularity in string cosmology. Okay. Now these were all nice heuristic arguments, but there were no equations. There's a missing dynamical description. And here we are going to provide a dynamical description which gives you non-singular cosmology. So now to motivate this, let's imagine running the universe backwards from now. The density rises, and eventually the density approaches string density. So at that point, string effects become important. So now I have to go slowly because now comes the key point. So now at the string scale, you get many new degrees of freedom which become equal in mass as the ones that you've included at low densities. All the winding modes, the momentum modes. And so if you want to have an effective theory, which contains all modes that are relevant, your theory has to include all of these new modes. So you have to change the effective action. And you have to change the effective action by a term which is localized on a space-like hypersurface, given by energy density equal the string scale. And this space-like relativistic hypersurface is called the S-Brane. Well, I call it the S-Brane. So here I'm introducing you to the main actor in the rest of this talk. Okay, so the effective action that I will be using is the following. It has this term, which is Einstein gravity. This is a Ricci scalar. So this term here is the usual Einstein action. This is the action of a scalar field. So this first line is the usual action for a scalar field coupled to classical gravity. But I have to now add a term which is localized at a particular time. So tau is this time. Tau b, that's a time when you hit string densities, and I will show that it gives you a bounce, and therefore I call it the bounce time. So there's a coefficient in this action, and this is the tension of this object, and the tension is given by the string scale. Eta s is a string energy scale. And this gamma is the determinant of the induced metric. So I take this metric, I pull it back to the hypersurface, and this is gamma ij is this induced metric, and gamma is the determinant of this induced metric. So I've now explained everything that appears in this S-Brane action. So this is the action that I'll now be considering. Okay. Good. So now the S-Brane can be viewed as a domain wall rotated in space-time. And if you imagine a domain wall, the domain wall has zero pressure perpendicular to it. And so this Wick-rotated object, the S-Brane, will have zero component of the energy momentum tensor perpendicular to its surface. And that's the time-like direction. So therefore the S-Brane has vanishing energy density. Since it's a relativistic object, it has tension, which is negative pressure. So you have something that has zero energy density, negative pressure, and that violates the dominant energy condition. And so therefore, with this action that I introduced, it is possible to obtain a non-singular cosmology, and in particular, it is possible to obtain a bouncing cosmology. So bouncing cosmology is a cosmology which starts out in a contracting phase, then it hits the string density, it passes, it hits the S-Brane, and it emerges in the usual expanding phase. So this is the bouncing cosmology which I will describe. So please ask questions if there's things unclear at this point.
Well, I wanted to ask a question earlier. When you were saying R is large or small or 1, you're using some measuring scale. Is it the Planck
String
length?
scale.
Ah,
string length.
So can you tell me what that is?
Well, this is the string length is a couple of orders of magnitude larger than the Planck length.
Ah, so it's not the Planck length. Okay.
There's another question from Geoffroy. Geoffroy, turn your microphone on, please.
So I'm just not sure of the argument that with which you claim that the S-Brane is precisely localized in time, because before you were referring to a tower of states that seems to appear gradually somehow.
Very good, but they appear very rapidly. You know, if the energy density is high, the universe expands very rapidly.
Okay.
So you get from 1/10 of the string density to the string density in very little time. Okay. And I'm approximating that by a distributional source.
Okay.
But now you could also ask, why am I putting a delta function and not a theta function?
Yeah.
Okay. Now the reason why I'm putting a delta function and not a theta function, that is because this S-Brane will generate a transition from contraction to expansion. So you hit the S-Brane, you pass through it, and you immediately start to expand, the density dilutes again. So this is why I put it in as a delta function source.
Just Thanks. One other point about the S-Brane. Why, I mean, you said it's a space-like hypersurface in 4 dimensions, so why isn't it a 3-brane?
Because the name 3-brane in string theory is reserved for a 3 + 1 dimensional object, which is time-like, which has time-like extent.
I see.
So, and also string theorists, Andy Strominger and Michael Goodpeller use the term S-Brane for something quite similar. Okay, any more questions here? Okay, so now you may think that a bounce in cosmology is very strange and unreasonable. And now I'll try to give you some arguments which should lead you to change your opinion. What I'll try to argue in the following is that actually it's inflation, a universe which only has inflation, that's a bit problematic. And a bouncing universe is not so problematic. Okay, but here I'm being rather opinionated, and I'll go back to being less opinionated when I get to the calculations. Okay, good. So here you see the space-time sketch of inflationary cosmology. So this is time. The vertical axis is time. The horizontal axis is physical space. And this is the period where space expands exponentially. And this is the pre-inflationary phase. So this is a Big Bang of inflation. This is the inflationary phase. This is the phase of standard Big Bang cosmology. This curve here is the horizon, the forward light cone of a point on the initial hypersurface. So during the period where space expands exponentially, the horizon expands exponentially as well. Now this solid blue curve is the Hubble radius, which is defined as the inverse Hubble expansion rate. Now, if you have exponential expansion, the expansion rate is constant, and therefore the Hubble radius is constant. So this is the Hubble radius. Now, this red line indicates the length scale of stuff which we observe in cosmological observations today. For example, the quadrupole of the microwave background, or structure on the scales of galaxy clusters, or structure on the scales of galaxies. So in this phase of exponential expansion, the wavelength of this structure increases exponentially. So if you go backwards in time, it decreases exponentially. So one of the reasons why inflation is successful is that stuff that we observe today starts out being smaller than the Hubble radius at early times, and therefore we can imagine a causal generation mechanism of these fluctuations. But the problem is that if inflation lasts only a little bit longer than it has to last in order to be a successful cosmology, then this length scale starts out at the beginning of inflation with a length smaller than the Planck length. And we know that effective field theory breaks down at least at that scale. So this is the trans-Planckian region of ignorance. So new physics must enter into calculation of fluctuations. Now, this fall, Waff and Bedroya turned this argument into a conjecture. And they argued that no trans-Planckian mode in cosmology can ever exit the Hubble horizon. So this is a trans-Planckian censorship conjecture, which actually originated from a talk that I gave at a Simon's string workshop in summer. Okay, so if we take this metric of space-time, the Hubble expansion rate, the Hubble radius is the inverse of this, then the trans-Planckian censorship conjecture means that if you start at some time t sub I with the Planck length, and you move this Planck length forwards to some later time, t sub r, then the physical wavelength that you get has to remain smaller than the Hubble radius at this time. Okay. Good. So now, one justification for this conjecture is an analogy with Penrose's cosmic censorship hypothesis, which prohibits super extremal black holes with mass, with charge greater than mass. So general relativity, as an effective field theory, allows for solutions with time-like singularities. It allows for black holes with charge greater than mass. Now, for such black holes, you can't set up the Cauchy problem in the usual coordinates, and an observer far away from the black hole sees the singularity. So these very bad aspects of these supercharged black holes. So therefore, Penrose conjectured that the complete theory will prohibit these supercharged black holes, which are allowed in the effective field theory, from arising. So now, the translation to cosmology is the following. The singularity of a black hole gets replaced by this trans-Planckian region of ignorance. The black hole horizon gets replaced by the Hubble horizon. So we are saying that the ultraviolet complete theory does not allow modes that were in the trans-Planckian region of ignorance to exit the Hubble horizon and to interfere with classical observables. And here I say some more words on that, but I think I want to go on. So that's one justification. The other justification is that effective field theory in an expanding universe is non-unitary. Because effective field theory, at least the way that I'm defining it here, it has an ultraviolet cutoff. The ultraviolet cutoff is at a fixed physical distance. And therefore, in an expanding universe, since modes are co-moving modes and the physical wavelength of a fixed co-moving mode is expanding, you have to keep creating modes. And so therefore, if you want to protect the observer, the classical observer, from this non-unitarity, you need the trans-Planckian cosmic censorship conjecture. So now, applied to inflation, it means that the period of inflation cannot last too long. And so there's a real tension between the trans-Planckian cosmic censorship hypothesis, which says that inflation can only last a small amount of time, and inflation being a source of what we observe today, which means inflation has to last for a long time. However, bouncing cosmologies are safe because modes never enter the trans-Planckian regime. So from the point of view of the trans-Planckian cosmic censorship conjecture, bouncing cosmologies are superior to inflationary cosmology. Okay, so now that I've given one argument in favor of bouncing cosmologies, I will introduce the Ekpyrotic scenario. And this is a bouncing cosmology described by a contracting phase with very slow contraction. And among all bouncing cosmologies, this Ekpyrotic scenario has advantages because it dilutes anisotropies, it creates spatial flatness, it's an attractor in initial condition space. And these are all the nice features which inflation has as well, at least if it's large field inflation. Other bouncing cosmologies do not have these nice advantages. So we are looking at the Ekpyrotic contraction. So, oops, there was, I think, one more. Okay, so the Ekpyrotic scenario is a phase of very slow contraction. So the scale factor grows very slowly in time. So time is negative in the contracting phase. P is a very small number. And in conformal time defined by this, it's given by this. Now, how do you get Ekpyrotic contraction? Well, like in inflation, you introduce a scalar field, which has a potential. Now, unlike inflation, it has to be a negative potential. And unlike inflation, it has to be a steep potential, not a flat potential. So this is a type of negative exponential potential, which will give you Ekpyrotic contraction. And these negative exponential potentials are ubiquitous in string theory. Okay, so if you take this potential, then this is the solution of the equation of motion for the scalar field. And you see that the time dependence arises inside of a logarithm. The prefactor is m Planck. And so you conclude that the scalar field moves only for a very small distance if t varies, let's say, for Hubble expansion time. So this model has the following properties. If you look at a Hubble time interval, the scalar field moves a very small distance. The potential has a large slope, and it has a large second derivative. Okay. These are completely different from inflation. In inflation, you need a very gentle potential or a very tachyonic potential, and you need very large field values. Okay. So now comes a second challenge for inflation. These are the swampland constraints. So if you stick to effective field theories, you have a huge landscape. Any space-time dimension goes, any number of fields goes, any shape of the potential goes, any field range is okay. Superstring theory is constraining. Only a small set of all effective field theories is actually consistent with string theory. The rest lie in the swampland. So you have this famous picture which says, if you come from this ultraviolet complete theory, then if you look at this huge landscape, swampland of effective field theories, only a small part is consistent with string theory. The rest is in the swampland. So what are the criteria of these little islands that stick out from the swamp? So the first criterion is that the effective field theory is only valid for a small field interval. The field interval has to be smaller than a constant of order unity times the Planck mass. And the potential of scalar fields that emerge has to satisfy these conditions. Either the slope is large or it is very tachyonic. Okay, let's go back to the Ekpyrotic scenario. Small field range, large curvature. So criteria are completely satisfied. So, good. Now let's look again at inflation. This is the equation.
Would that be a good time for a question? John has one.
Let me say one more thing, and then I will interrupt. So for inflation, you need a very shallow potential or a very tachyonic potential. And so these conditions are exactly the opposite of the swampland. And so therefore, you conclude that slow roll inflation is in the swampland, but bouncing cosmologies, in particular, the Ekpyrotic scenario is not in the swampland. And that creates more motivation to consider the Ekpyrotic scenario. So, John?
Yes. I just wanted to say that Bert Overhout was my classmate. So is that the Ekpyrotic thing you're talking about?
Yeah, that's what this is his contracting universe. In fact, you see, you mentioned his name. His name will appear in one of the next transparencies.
Okay, but that's not actually my question. I was just shocked because I never really studied his Ekpyrotic universe. I guess it's Steinhardt and Turok and Overhout.
And Curry.
All right. Anyway,
but I'll explain it now.
But I thought it was something really scary, something with
Well, it might be scary. Let me explain it to you, and then you can decide if it's scary.
But I just saw something scary on your slide. Do you really mean a negative decreasing exponential?
Yep.
But that means that phi, if it's real, it's completely unstable. It's flying towards minus infinity.
It doesn't get to. It's only a negative exponential for positive values of phi.
Ah.
Once the density hits the string density, things change.
Oh, I see.
And that's where my equations enter.
So is there some kind of equilibrium point?
You will see. You will see.
Okay.
Okay, so the challenge, so John mentioned that the potential in the Ekpyrotic scenario is unbounded below. So therefore, how does one get a bounce? How does one get gravitational waves? How does one get cosmological perturbations? These were all not so well understood before our work. In previous realizations, you needed new strange matter to obtain a non-singular bounce. This matter also was needed to get perturbations which are observable, and you always got negligible gravitational waves. Okay. Now in our work, what we've done is we've included the S-Brane, and that gives us automatically a non-singular cosmology. And the late time equilibrium point is going to be an expanding universe that expands very slowly. That's the answer to your question, John. Now, we discovered that gravitational waves passing through the S-Brane acquire scale-invariant spectrum. Cosmological perturbations acquire scale-invariant spectrum, and that's good for observations. And we get two consistency relations between the four basic cosmological observables, which means that the model is falsifiable. Okay, so now I come to the last part of the talk, where I actually discuss the calculations. So first I will discuss the background evolution. So the action is the action I showed you before of a negative exponential potential coupled to Einstein gravity, but in the presence of this S-Brane. Now, if we match the metrics, the background metrics, above and below the S-Brane, then we need continuity of the induced metric and a jump in the extrinsic curvature, which is given by the tension of the S-Brane. These are the generalized Israel matching conditions. And so the jump in the extrinsic curvature tells us that the Hubble constant changes by an amount which is proportional to the tension. This is positive. Before the bounce, H was negative. If this is sufficiently large, after the bounce, H is positive. So this distributional source that you add to the action gives you a non-singular bounce. It's obviously not a smooth bounce, but it is non-singular. So n has to be larger than m Planck over eta s. So in order to have delta H be sufficiently large. But the string scale is typically very close to the Planck scale, so this constraint is quite reasonable. Okay, so result number one, the S-Brane gives us a non-singular bounce. Okay, so now we come to the part of the talk, which for a cosmology audience would be the main stuff, but here I'll go quickly. So we are interested in following gravitational waves as they start out in the contracting phase and as they start out in the vacuum state. We want to follow them through the bounce to the present time and compute what is the amplitude of gravitational waves and what is the spectrum of gravitational waves, which we predict. Okay, so this is the gravitational wave tensor. It's a spatial tensor. I took a gravitational wave traveling in x direction. So therefore the gravitational wave tensor is in the YZ plane. This is the polarization tensor. This is the amplitude of the gravitational wave. And the amplitude of the gravitational wave, or the rescaled amplitude, obeys this simple equation of motion. I wrote it in Fourier space. It's a linear equation. So each Fourier mode is independent. And okay, you see that for large wavelengths, there is an instability. And the instability is larger the wavelength. Okay, so now you can study this. So you can study the gravitational waves in the contracting phase, and you find that an initial vacuum spectrum remains vacuum because this gravitational wave amplitude hardly changes. Okay, let me jump forwards. Good. No, I won't jump forwards. I'll continue the way I planned. So now the cosmological perturbations, they are perturbations of the metric that couple to matter. They have this form. So this is now the four-dimensional metric. This is the metric perturbation, which couples to the matter perturbation. This is a variable in terms of which the actual cosmological perturbations has canonical form. And this variable V satisfies this equation of motion, which is the same equation of motion as that of gravitational waves. And so therefore you get the same conclusion that the V variable retains a vacuum spectrum at the end of a contracting phase, like the gravitational waves. Okay, however, you can also look at phi, which is the thing that we observe today directly. We can rescale phi, and then this variable phi behaves very differently than the variable V. In particular, this variable phi has a decay mode, sorry, a constant mode in the contracting phase and a growing mode in the contracting phase. And the vacuum spectrum of phi is transformed into a scale invariant spectrum at the end of a bounce. So for cosmological computations, we need to know how do gravitational waves pass through the bounce, and is it V or U which is continuous through the bounce. So previous studies with smooth bounces showed that gravitational waves remain vacuum. Oops, I did a mistake. Can you still see my screen?
Yes, we can. You're
Okay.
at the key question, page 49, out of 60 of your talk.
Good. Now the problem is that I lost my own screen. Okay. I can only see you. So, good.
Why don't you stop sharing your screen and resume, Justin?
Yep. Good. And I'll bring back. Okay. Good. Now I have my own screen again. Good. So the key question is which variable passes through the bounce continuously? And previous work, it was always the variable V which passed continuously, and therefore you didn't get any good results for observations. So, what we did is we first studied how gravitational waves pass through the bounce. And what we discovered is that gravitational waves passing through the bounce obey a very interesting harmonic oscillator equation with a time-dependent mass which has a distributional source. And so the way you can treat that is you can solve the equation of motion on both sides of the bounce, and then you can match at the bouncing surface. And you get, it's a typical mode mixing calculation, and you get Bogoliubov coefficients. And well, you find that the Bogoliubov coefficients which describe how the modes are coupled have an m over k factor, which is an amplification of long wavelength modes. And that's exactly what you need to transform a vacuum spectrum into a scale invariant one. So therefore, gravitational waves passing through this S-brane obtain a scale invariant spectrum with a slight blue tilt. And this is what we never had in previous realizations of the Ekpyrotic scenario. And so this is the power spectrum of gravitational waves. This is what astronomers would like us to calculate. So now for curvature perturbations, we followed we looked at the variable phi, which has this growing mode in the contracting phase. In the expanding phase, this is a decaying mode, and this is the dominant mode in the contracting mode. In the expanding phase, it's constant mode. And so we need to study how the matching across the S-brane connects A plus to B minus. If there's a non-trivial connection between A plus and B minus, then we get a scale invariant spectrum of curvature perturbations. Okay? So the matching conditions were worked out by Durer and Venizzi. And they found these relations between the coefficients in the contracting phase, A minus and B minus, and the coefficients in the expanding phase. And you see that B plus, which is the thing that we want to compute, depends non-trivially on A minus. And therefore, we are successful at getting a scale-invariant spectrum of curvature perturbations. And if we start with initial vacuum perturbations, we get this amplitude of the curvature perturbations. Scale-invariant, but with a slight red tilt. Okay, so I don't expect you to have followed all the calculations, but just the basic results. And with these basic results, we can go to our observer friends and make two predictions. The first prediction tells us that the amplitude of the gravitational waves divided by the amplitude of the curvature perturbations, which we've observed, is given by the slope of the spectrum of curvature perturbations, which has also been observed. This N sub S has been measured to be 0.96. And the amplitude of the scalar perturbations has been measured. And so this is a prediction for the amplitude of gravitational waves. It says it's about 10 to the minus 4 of the amplitude of the cosmological perturbations. And the second prediction is that the tilt of the spectrum of gravitational waves is blue and not red as it is for inflation. Blue means easier to find. And its magnitude is given by exactly 1 minus the slope of the scalar spectrum. Okay, so these are two predictions which are toy model based on an S-Brane bounce makes. And so now I'm almost out of time, but I'm also almost at the end of the talk. So I want to end with the conclusions. So I hope to have persuaded you that using this distributional source, this S-Brane, this allows us to circumvent the conclusions of the classical singularity theorems for cosmology. It allows us to get a transition from contraction to expansion. And if you apply this to the Ekpyrotic model of contraction, then we get naturally a transition between Ekpyrotic contraction and standard Big Bang expansion. And in this setup, we found that gravitational waves passing through this S-Brane acquire a scale-invariant spectrum with a fairly large magnitude and with a slight blue tilt. And we found a scale-invariant spectrum of curvature perturbations with a slight red tilt, like has been observed. And we get two consistency relations between the four basic cosmological observables. So this is a connection between generalized functions, ordinary differential equations, cosmology, and observables. And the upshot of this for the pre-talk discussion, John, is that time can be past eternal. So thanks for listening. So questions?
I'd like to know if the bounce can repeat itself. So can there be multiple bounces, or is there a single bounce in the whole universe?
Okay, it looks like there's a single bounce. And the reason for that is current observations. Current observations indicate that there's something that is dark energy, and that will prevent the universe from contracting again.
I had a question again.
Go ahead.
Is the S-Brane compact?
No, I take it, well, if space is compact, then the S-Brane is compact, yes.
But in your model, space is a torus.
Yes, that's right. So the S-Brane is compact.
Okay, now, I don't know if I understood this at all, but is the S-Brane somehow the lower bound? Is that what it's contracting to?
Lower bound of what?
Of the spatial universe.
Yes, when the universe hits the S-Brane, it has smallest spatial extent.
And then it expands.
then it expands. But it has a finite extent, not zero size.
Right, right, right. And there's no, I mean, it's not a singularity, it's just simply a bounce.
Right. It's a distributional source. So we're not dealing with smooth functions, but we are dealing with well-defined generalized functions.
Okay. The reason why I found Ekpyrotic scary was the way that Bert described it. He said that it was something that was extremely hot and chaotic. Which end is hot and chaotic?
Well, you see, the string scale is quite high. So you wouldn't want to live on the S-Brane.
You wouldn't want to be on the S-Brane. It's pretty.
You wouldn't want to be on the S-Brane. So
okay.
it's
So
not a
even though
nice
it's
place.
not a
But similarly, you would not
singularity,
like to be in the inflationary phase.
Okay.
Because
What
the
about
energy
the
density is similar than there.
Uh-huh.
So both are scary in that sense, but from a mathematical point of view, there's nothing to be scared of.
Okay. So did you say you're writing a paper together with him?
No, no. So the paper is written, or we have a series of papers. But what I presented today, that's already written up.
Oh, okay.
Geoffroy has a question now. Geoffroy?
Yeah. So just to confirm, because maybe I missed this part, but at the end of the day, in this model, the evolution of the matter field stays completely unitary when it does across the bounds?
Okay, now this is going to be the third of our papers.
Okay.
So the evolution of the matter fields across the brane, this is something we have not yet studied in detail. What will happen is the brane will mediate the transition of matter from this phi field to the usual radiation.
Mm-hmm.
So we will get the usual standard model matter after the brane. But this is partially wishful thinking. It is not yet completely worked out equations.
And, another question I would have is how much of this is dependent on the actual use of string theory? Because I mean, it seems like you're mostly using the fact that you have this tower of new states that appear when you approach this S-Brane, but do you need the rest of the framework in a way, except just as a confirmation that it sits well, then it's not in the swampland? And I don't know.
Well, see, the only way that I can justify this exponential tower of states is from string theory.
Okay.
So it doesn't mean that you couldn't justify it in other ways, but
mm-hmm. Thank you.
John, do you still have a question? Your hand is raised.
Oh, I didn't mean to have my hand raised. I didn't have another question.
Okay, no problem. So I apologize to Robert. I lost connection a few times during your talk. So I'm sorry, but we should thank the speaker. I'm invited people to turn on their microphone and give a raise to thank Robert if there's no more question. Thank you, Robert. Nice talk. And next week is the last talk of the series for this term. It will be Théopinet on a more mathematical subject related to representation theory of the affine temporally lead on the chain spin XXZ. So thank you all for joining us. Thank you, Robert, for the talk.